So we just kind of finished quantum mechanics. And I really like that section on quantum mechanics because it takes something that you kind of learn in PChem and gives you some few tools to actually get some practical things out of it. And we can actually get more practical things. We'll see in a little while. We can get a lot of things like heat capacities of ideal gases, or the enthalpies of formation of ideal gases, or the entropy of ideal gases. You kind of saw that in the thermal properties. And this is a powerful thing. In fact, we think we're so good now in terms of computational chemistry, if we use the fanciest theories and basis sets, which we can do on a fairly regular basis, that we are as good or better than experiment now in terms of ideal gas heat capacities and entropies and heats of formation. So these are things that are kind of important whenever we do thermodynamic calculations. We often, like when you're doing the change in enthalpy across a compressor, you need the heat capacity, right? Because the temperature is changing and it's a gas. And you usually make some sort of thermodynamic path, right? Where you go down to low pressure, so you can use the ideal gas heat capacity. Then you do the change in temperature, and then you go up to whatever pressure you're talking about. You should remember that from thermo, right? These thermodynamic cycles where I'm going, either I'm expanding over a valve, or I'm going through a compressor, or I'm going through a turbine. You did this down to low pressure, do the temperature change up to whatever pressure you're going to, or down to whatever pressure you're going to. And that way you can use the ideal gas heat capacity. And that's what we typically, for a gas state, that's what we typically tabulate in any books. We don't calculate or tabulate heat capacities for gases at 10 bar and 11 bar and 12 bar and 13 bar and 14 bar, right? You don't see that because it's way too much tabular thing. And we can use these thermodynamic integrations, these paths, to do what we want. And so it's okay that we have just ideal gas. And when I say it's an ideal gas heat capacity. Now the question I have is, why am I saying it's ideal gas? I keep saying that quantum mechanics gives us ideal gas. Any ideas on that? It's actually fairly obvious if you think about it, but why am I saying quantum mechanics, what we've been doing, gives me the ideal gas state? Tyler?
Probably because you're trying to ignore molecule-molecule interactions.
I have. How did I do that in my computation, I guess?
By not including it in your sum of Q's.
That's right. I just only have one molecule in there, right? We've only built, say, like a methane molecule. All we built in Gauss view was one molecule, right? Or when you did monoethanolamine, or when you did acrylamide, all you did was one molecule. It's kind of by definition ideal gas, right? There's no other molecules affecting it. And so the property you get is for ideal gas. And that's why I keep saying ideal gas. What would I have to do to get non-ideal gas, where you have interacting molecules? I'd have to stick another methane molecule in here. And in fact, I'd have to stick a lot of methane molecules in here. I want to get close to, thousands or tens of thousands, or Avogadro's number of molecules. And then what happens to my computations? It becomes impossible. And so there are some ways to do condensed phases that we don't talk about. It's not really used because it's not great. So what do we do to start looking at real gases or condensed phases like liquids, where I have lots of molecules that are really close together? Kyle probably knows this because he does it. What do we use, Kyle?
I'm thinking molecular dynamics.
That's right. We have to go to a different technique. And one's called molecular dynamics. Or we could do a Monte Carlo simulation too. We're going to talk about both of those in this class. But whenever we go to molecular dynamics to Monte Carlo from, say, quantum, we often talk of going up in length scales. or I need to simulate a bunch more molecules. And so instead of looking at the electron level, which is kind of angstrom or sub-angstrom level, I'm going to, my length scale is kind of above that now. I need to start ignoring the every electron, and I'm just going to start considering atoms as a whole unit. I have a hydrogen atom rather than I have a hydrogen proton and a hydrogen electron. Does that make sense? So you'll often kind of hear this term that I go up in length scales. And then above this, molecular dynamics, we can even start going a little higher. Maybe instead of having a methane as 5 atoms, I have a methane as a super atom, or a coarse grain atom, as you'll hear that term. I group atoms together. And I kind of showed you some of that on the first day with my DNA model. Remember, I had modeled DNA has like a phosphate backbone with oxygens, and then you have an oxygen here, and one of these this goes to a sugar ring, and then off this sugar is this aromatic nitrogen base. And I said, I'm going to model this. I'm going to group all these atoms together. I'm going to group all of the sugar atoms together, and I'm going to group all the base atoms together. And so I've gone up in length scale again to save computation. Does that make sense? Because DNA can get really long. Right? Our DNA in our, if we unrolled the DNA in one chromosome, right, it would be like a micron or a meter long. And then it's all compact down into our cells. But the point is that I've gone up in length scales again. So I start, the lowest we ever start kind of for practical chemists, chemical engineering or chemists is, right, atoms and electrons, protons and electrons with quantum. You could go to quarks, right, and all the subatomic particles. That's what physicists usually worry about. We don't ever need to go to that level to describe chemistry. So the lowest is quantum level at the angstrom, where I'm doing, electrons and protons, and I solve out Schrodinger equation. The next highest length scale is when I'm going to look at individual atoms as a whole. And I can parameterize or start to make a mathematical model for how a hydrogen interacts with a hydrogen atom, how a hydrogen interacts with a carbon atom, and how it bonds, and things like that. And then I can also go across atoms, right? This hydrogen interacting with this hydrogen interacting with this carbon. And then if I wanted to go higher than that, I would coarse grain several atoms into supergroups or coarse grain groups. And then kind of the next level is what we call continuum. This is what Dr. Lignell does, where he doesn't actually simulate atoms, right? He simulates fields, or like reactions when he does CFD. We don't actually put all the molecules in there. We just kind of look at them as a field. We know if we have, say, a plate that's moving or a flow of liquid across the plate, we have some of these continuum, right? Navier-Stokes-like equations that describe this. So you can go all the way from, say, atoms, or let's even say electrons, to atoms, that's the next length scale out, to coarse grain atoms, or super, coarse graining or super atoms, or sometimes this is also called united atom. There's all sorts of variations on the theme. Like sometimes I'll just get rid of the hydrogens, or I'll lump the hydrogen with the heavy atom, because there's lots of hydrogens and things, but often they don't really do much in terms of phase behavior. And then I've got continuum, where I'm looking at, partial differential equations in the X, Y, Z type Navier-Stokes equations. So we started here down in electrons, and even for small molecules, it takes a long time. Tyler, what's your question?
When you go from one length scale up to the next, when you are collecting the data needed for the next scale, do you use empirical data, or do you use the results of your simulations one scale down, or does it just depend?
You can do it both ways. So, and people try both ways, and and there's pros and cons to each one. Basically what Tyler asked is we call it top down or bottom up. So let me give you an example. I could theoretically run a quantum calculation of two methane molecules coming together. And I could put them at, say, 1 angstrom apart, and then 2 angstrom apart, and then 3 angstrom apart, 4, 5, 6, whatever. I could get the energies and map that out. What would that look like? If I plotted those energies out, right? You could do this. I could give you enough time. You could use Gaussian. You could select a level of Therian basis set, and you could do this, right? And just mark the energies out. And you could convert them to kilojoules per mole or something that we like to talk about instead of Hartree, whatever. But what would that energy look like? You actually know the answer to this. You might not realize you know it, but as I bring two molecules together, what's the energy look like?
Wouldn't it look like the Leonard-Jones equation of state?
Exactly. It looks like Leonard-Jones. Leonard-Jones looks something like this. If I graphed the energy between the two molecules as a function of the distance between them. And this would kind of arbitrarily be set at 0. When they're far away from each other, they don't feel each other. As they start getting closer, because of dispersion forces, which are caused by electron correlations, right? I randomly kind of get all the electrons on one side of the molecule, so I get an induced or a small dipole, and then the other one can get a small dipole, and that is what brings these two together. And so this is the dispersion force. The energy goes down as they get close together. But then if they get too close together, what happens? Then they start to overlap molecular centers, right? The protons start overlapping with the protons, right? And then they repel each other because things don't like to be on top of each other. And so Leonard-Jones, this is how you spell Leonard-Jones, is a model, a mathematical model of what you would see if you did the quantum. So I could go in with the quantum and I might have a point here and 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 a point here. Leonard-Jones, U is equal to 4 times epsilon sigma over r to the 12th minus sigma over r to the 6th. Leonard and Jones proposed this mathematical model to describe that phenomena. And so then I could just do a least squares fit and get the sigma and epsilon for two methane molecules coming together. Does that make sense? And once I had this model for two methane molecules, then I could stick a lot of these methane particles into a simulation box. And that would be kind of this coarse grain approach, right? I'd stick a lot of these CH4 molecules in here, and I would have them interact with this U potential. And I can watch what happens. And I can make my box lengths. So I'm actually going to, put this in a 3-dimensional box. I could set the box lengths relative to the number of particles I put in here to get a specific density. And then I can map that to something that's realistic, right? N divided by volume, I can get a realistic density, and then I could calculate, say, the pressure at that density. And I can start to predict thermal physical properties for methane.
What were sigma and epsilon again?
Oh, that's good. So those are the parameters in the Leonard-Jones. Sigma is about the width of this well. It's actually like 2 to the 1/6. If you go through and take the derivative of this, set it equal to 0 to find where the minimum is, it's like 2 to the minus 1/6 sigma is where the minimum is, something like that. But
so
it's about the width of a molecule.
Distance?
And then epsilon is the depth of this well, is what it comes out to be.
And so if you were trying to predict like heat capacity, would you use a coarse grain model?
That is a good question. So if I would probably use this length scale, where I'm at least representing all the heavy atoms. Because let's go down a little bit. What would happen? Where do you think this idea of modeling everything as a Leonard-Jones superatom, where does it break down? You could think if I had a pentane molecule versus a methane molecule, approximating this as a sphere, right? I should move this one down, is way different than approximating a methane molecule as a sphere for Leonard-Jones. Does that make sense? This one will not be as accurate, but theoretically I could do that, right? I could stick these molecules into my Gaussian, a pentane molecule, move it in, bring it further away, map out a bunch of points that would look, you know, something like this maybe, and then fit a Leonard-Jones potential to them. But I'm not going to be super accurate. So give me some ideas. What would you do then to fix this problem? Leonard-Jones supermolecules work well for spherical particles, but not for elongated ones. And we have a lot of elongated things we care about, right?
You could use the eccentricity factor or whatever.
Okay, I could. There's actually, I could maybe start modeling this as a ellipse. There's ways to do that. In fact, somebody called, that's called the Gay-Byrne potential, is when you've got some sort of ellipses. But what modern simulation does is probably model a CH3 group and a CH2 group, because those look kind of spherical, right? So instead of just having one pentane group, I'll make a pentane molecule out of two CH3 groups and three CH2 groups. That's one way. In fact, that's for hydrocarbons, that's kind of state of the art. I lump the hydrogens in with the heavy atoms. And I could even start talking about more complex molecules, right? Like a isopentane or something like that. I could have a CH3 group, a CH group, and I guess let's change colors. I could have two CH3 groups, one CH group, and then one CH2 group, and then here's another CH3 group. So I could have a Leonard-Jones for a CH3, you know, and it might look like this, and have an epsilon and a sigma that go into its. And then I would have to do something for CH2s, which will have a slightly different epsilon and sigma, because a CH2 is a little different, right? It's a little smaller, so sigma will be a little different. And then you could imagine starting to do oxygens, right? Maybe this is a ketone instead of a isopentane. I could start modeling a double bond oxygen and a carbon next to a double bond oxygen. And you can see how I start having to get epsilons and sigmas for every possible atom I care about. That's
Dr.
actually what
Nance,
we do now.
wouldn't you have to, because it looks like you have like a Leonard-Jones for CH3 and then one for CH2. Wouldn't you need one that's like how a CH2 corresponds with the CH3? So it's not so much the molecules you want to, it's the bonds that you want to model.
Okay, we'll get to bonds too, but what about if I have, let me answer both of these questions. Let's say I have another, I'm gonna make this isopentane again just to make it a little easier to see.
Yeah, when you're saying do Leonard-Jones for, CH3, what you drew in the yellow orange over there, does that mean like just the interactions between two CH3 molecules? Okay.
Here's what we do is we would you guys are on to two important things you got to figure out. So I would, in my Gaussian, I would put a CH3 group in, and I'd put a CH3 group in, and I would start bringing these together, a distance R, get the energy, change the distance, get the energy, change the distance, get the energy, change the distance, get the energy. And then I would have the CH3, epsilon, and sigma. So anytime a CH3 interacts with a CH3, then I would know what that epsilon and sigma are. In fact, I'm going to put two different molecules in here so you can kind of see what I'm talking about. CH3, CH, CH3. So this potential would be, tell me how these CH3s interact on different molecules and how they interact on the same molecule if they're kind of interacting. It's unlikely that this CH3 would interact with this one because it's so close. I'll talk more about that in just a second, but I would get a CH3 interacting with a CH3. But I think someone, maybe Matt pointed out, what about this CH3 interacting with this CH group? What do I do there? Or the CH3 or this CH2 interacting with this CH3, right? You've got these cross interaction terms. It's one thing to say, I could say CH3, CH3, CH2, CH2. That's what Leonard-Jones will give me. There's two ways to approach this. I could theoretically go in my Gaussian and take a CH2 and a CH3 and then start bringing them together and then get a CH2 to a CH3 Leonard-Jones. Does that make sense? I could get an epsilon and a sigma for that. And then I could do a CH2 with a CH group. And this will be a different epsilon and sigma, a little different. And then you can start getting nitrogen groups and oxygen groups, but that's not what we do in simulation. Instead, what we do is we have what are called mixing rules. Some people call them combining rules. These are not the same that you might learn about in macroscopic thermo, where you were doing multi-component phase behavior and getting phi's. That's not what we're talking about here. They kind of look similar, but what this is talking about is how do I, if I have a CH3 interacting with something that's not a CH3, say a CH2, how do I describe that interaction? I am still going to use a Leonard-Jones equation. I guess I could say equation form. I'm going to put, this is going to be, I'm going to call this mix, epsilon mix and sigma mix. When it, just to denote that this is this cross term. It's not the CH3 with the CH3, it's a CH3 with something else. And what I would do to get, oh man, I don't know why sometimes it zooms in like that. And what I would do to get this epsilon mix is take the square root of epsilon I, epsilon j. Or in this case, my example, it would be epsilon CH3 and epsilon CH2. And this is what I would stick in here to do a cross term. And then what would I do for sigmas? I would say sigma mix is equal to sigma I plus sigma j. This is the arithmetic mean over 2. Or in our case, the CH3 plus the sigma CH2 over 2. So this is geometric mean. And this is arithmetic. So if I just have the pure component sigmas and epsilons. I can get the mixture sigma and epsilons using what are called these mixing rules or combining rules. Now, let me say something. This is not exact, but we found that it's good enough. It would be best if you go in and do a quantum Gaussian calculation for every possible combination. But that is just prohibitively costly when you get all the possible, say in a protein, right? You've got nitrogens and oxygens that are single bonds and oxygens that are double bonds and oxygens that are linked to carbons and oxygens that are linked to nitrogens and nitrogens that are linked all over the place. You got aromatics, you got rings. And so you don't do that. You do the pure component ones, and then you can do everything else with mixing rules or combining rules. Different people call them different things.
So Dr. Notch, just to clarify, this, what we're talking about is modeling how a CH3 of one molecule reacts with a CH3 and a CH2 of another molecule. Is that right?
Yes, or it could be on the same molecule. So let's talk about that for a second.
Around. Okay.
Yeah, let's talk about this for a second. What we usually do I'm going to put a pretty long molecule in here. I don't know what that is. Is that 8 carbons? 1, 2, 3, 4, 5, 7. So I've got this heptane molecule. As hydrocarbons or molecules get longer, right, they can wrap around and interact with themselves. Does that make sense? In fact, as they get really long, they really like to do that. They do not stay straight. That is a entropically disfavored state, right? They like to be mixed up. And so it is conceivable, right, that this CH3 could interact with the same CH3 molecule on the same, or the CH3 on the same molecule. In fact, I'm going to put 2 of them down here. So when I say you have an epsilon for CH3 and a sigma for CH3 that you're going to put into your Leonard-Jones, it describes, in general, a CH3 interacting with CH3s anywhere in the system, even if it's on the same molecule. But there's an exception. We don't calculate those Leonard-Jones dispersion interactions for anything that is bonded or that is 3 bonds away or 2 bonds away, or it's an angle. We call it a bend because I'll show you in a second. So I would exclude, let's look at the CH2s for a second. If I'm trying to look at how this CH2 interacts with all the other sites in this system, I would not have it look at this one or this one because they're bonded. And I wouldn't have it look at this one or this one because they're 2 bonds away. And the reason we do that is just purely mathematical in the sense that those are governed by the bonds between and not by dispersion interactions. And so we call it 1, 2, 1, 3 exclusions. And sometimes some models do 1, 4 exclusions, but typical is 1, 2, 1, 3 exclusions. Exclusions. And we're going to review all this when we start getting to molecules here a little later, but I'm glad that you guys are thinking about this. This is what I want to get out of this lecture. Go ahead, Tyler.
So
how do you model the bond itself? Do you just fix the length? Do it?
Okay, so how do we do the bond? I think Matt asked that early. How do we model a bond? How do we model it quantum mechanically? Does anyone know? Well, I guess no, I shouldn't even say quantum mechanically. Well, we do. What do we do quantum mechanically for vibrations? I don't know if I'm asking.
Harmonic oscillator.
Harmonic oscillator. What's a harmonic oscillator look like mathematically?
like mathematically is like a sine wave kind of, right?
So it is like a parabola. You guys kind of remember seeing energy levels for vibrations written something like this in your PChem class? It's not exactly a parabola because it's actually asymmetric a little bit if you kind of do the quantum, but it's so close that for anything that's low level, unless you get up to, you know, excited state number 10 or whatever, for ground state, I'm just going to use harmonic oscillator. And what's the mathematical equation for a parabola or a harmonic oscillator is I'd have a K value and it's R minus R naught squared. Or if I have a C bonded to a C, R is the distance, and then R naught is the equilibrium distance. I know on average how far a C wants to be away from a C. And then I can know how wide this is from some sort of vibrational spectra and fit the K value. So I model a bond basically as a harmonic oscillator or a spring, if you want to talk macroscopic, right? It's just a spring between two atoms. And so this kind of goes back to the 1-2 exclusion. If I'm modeling two atoms that are next to each other with a spring, I don't bother to do Leonard-Jones, right? Because it's bonded. Now, what about, so this is great. We've got a mathematical model for bonds. We have a mathematical model. I don't know where my last Leonard-Jones one is. This is a mathematical model for non-bonded or dispersion interactions. Right, that's the whole electron-electron correlation. There's some other intra, T-R-A, so inside the molecule, there's some other interactions that you don't quite see the way I've drawn it here, but right, a water molecule has bonds, but it also has a preferential angle, right? That things like to be. Alkanes have the same thing, right? Because they're tetrahedral type looking things with carbons. There's a preferential angle that you want to make sure you maintain. How do I do that? For lack of a better thing, we just use a spring in angle space. Call this like a K theta. And so I just keep that restrained to its equilibrium angle, which we know, right? We kind of know what a water molecule is. We know what a tetrahedral angle would be between these hydrogens. We know what that is. And so we can get a different K theta and theta naught for each one of those. And I keep track of every single bond and every single angle in my whole system. Now there's one other intramolecular feature that we want to keep. What's that? In fact, I'll give you a little hint. Bonds are 1, 2. Angles are 1, 3. We call these angles or bends.
The dihedrals
are 1, 3. And then the last thing is the dihedral, or you'll often hear torsion too, right? Torsion potential. These are 1, 4. And this is, right, a 4-body interaction where I spin around that central bond and it's looking at the angle. You see, what do they call that? Neumann projections back in chemistry? I haven't used them for so long, where you have like gauche or eclipse. Do you know what I'm talking about? Like you'll see something like this drawn like this, like for ethane. You guys remember that? Or we've talked about them with Gaussian. I got to have a torsion angle where I can have, this is the trans versus cis. Sorry, that should be a phi. I want to keep things that want to be trans, and I want to keep things that want to be cis, or I want to keep things that are eclipse, or whatever. And so I also need a dihedral torsion. And that's what one of the problems are for chapter 4 projects, right? We kind of talked about that last time. I can make an ethane molecule in Gaussian, spin that dihedral around, and I will get some sort of potential that looks like this, where when they're not eclipsed, it's really low energy. And then when they're totally eclipsed, it's the highest energy. And it kind of goes through that 0 to 360 spin. These dihedral torsions, we often model with some sort of cosine expansion, kind of like we talked about last time. And it might just be one cosine term. You could square the terms. You cannot square the terms. Sometimes it might look like 1 minus cosine of n theta. That's how some models work it, but it doesn't necessarily matter which form you use as long as it is cyclic like this. So I can go through and build up mathematical simple models, fairly simple, right? Cosines, parabolas, squared terms, right? For my bonds and my bends, and then Leonard-Jones for my non-bonded interactions. And if I keep track of all the positions of all the atoms in my system, right? If I go back here, I'm keeping track of all the positions of all my atoms in the system. I can determine what all the forces are. How do I do that? How do I get the forces? And then once I have the forces, I can just use F equals ma to move the system. Just normal Newtonian physics. That's what molecular dynamics does. It defines all these potentials. So my non-bonded dispersion, my bonds, my bends, I should put bends right. My torsions are going to look something like, whoa, let's get rid of you. That's what happens when you try to use your fingers and your pen. My torsions, I can define all these, and then I can calculate all the forces on the system from the potential energies, and then I can move the system with F equals ma. And what I do in molecular dynamics is I move it, say, half a picosecond, and then I have to reevaluate all the forces again, move it another, well, I actually want to do half a femtosecond, sorry. I want to do half a femtosecond, move everything, move another half femtosecond, move everything, move another half femtosecond, move everything. So I do this in the computer, right, to see how things evolve. Now, how do you get the forces from the potential energy? I don't know. How do I go from potential energy to forces? Anyone know that?
You can kind of, the way I look at it is the potential energy is kind of like a field. So like I see it as like a, kind of like a landscape.
Yep.
And then the force is kind of pushing you down the landscape, or like pushing you around on that landscape. So you can take a gradient of the landscape, and then it should be related.
That's exactly right. You take the gradient, you take the derivatives. So, right, if I have a ball that's on a hill, the forces want to drive it down here, right? How do I know that? Because it's the gradient of the potential energy. And so literally, if I have a U value, the way I get forces is I take minus du dx. This will give me the force in the x direction. And then if I want the force in the y direction, because force is a vector, right? I need x, y, z. Force in the y direction is du dy. Force in the z direction is du dz. And we'll go through another day on how we do these derivatives. But it's possible to do these derivatives. They're not super hard, right? I know how to take derivatives of cosines. I know how to take derivatives of parabolas. And I even know how to take derivatives of things that are r to the minus 12, r to the minus 6. So I can get all the forces in the system. And so I just use Newton's equations of motion and move things through time. I know F equals ma, I get an acceleration. I know how fast they were going. And so I can evaluate my ordinary differential equation with some sort of small time step. And for the time step you have to do for molecular simulation is very small. It's on the order of half a femtosecond. And so it takes a long time. This is fantastic. We've gotten through a lot of good stuff today. What time is it? Okay, 10:18. Now, I had a minor crisis this morning with this class. If you look at chapter 5, in fact, I'm going to bring up chapter 5 and chapter 6. Hey, can I say one thing? I hate it when I look down and you see how bald I am. You see that? That's the lamest thing about Zoom, especially when I got a camera on there. I can't wait.
That's why my camera's always off, Dr. Knotts.
Man, it's ridiculous. I don't know what to do. I'm like, oh, every time I catch my picture, I'm like, dang, I'm so bald. So much balder than I was 10 years ago. Let me bring up the book here. And don't be worried if you didn't catch everything we talked about. We're going to go over this again and again, right? This is some new concepts. But this is kind of the overview of where we're going. Chapter 5 sets up. The whole purpose of chapter 5 is to take a whole statistical mechanics class and basically condense it into one chapter to get you what we call the partition function. And so we go through a lot of stuff. In fact, I told you to bring some coins so we could do this little example of, out of all the combinations, what is most probable when you start flipping coins. And if I flip it 10 times or 100 times, I don't necessarily want to talk about that right now. But that's the whole reason we do that is because we need that concept when we develop the partition function. We have another thing that we've got to do. We talk about this Stirling approximation, which allows us to calculate the factorial of a very big number, like 6 times 10 to the minus, 10 times 10 to the 23rd. And then we start talking about postulates of thermodynamics, here's this thing we just talked about. How do you get the force? You take the minus gradient. So that's how we talked about that. Talk about Hamiltonian. All this stuff we talk about and then distributions is to get down to this partition function derivation. Right here. To get down to this equation right here. Now, it takes me 2 days to do that. It's so boring. And I don't know if it's super useful in terms of practical simulation. Because in the end, we recognize we can never know this for anything that's not ideal gas. Okay, we can know it for a hard sphere. You guys know what I mean by hard sphere? It's like billiard balls. I just assume that it's infinite potential if they're overlapping. It's zero if they're not. And we could technically solve it out for Leonard-Jones in certain cases. But what we do is because we can't solve that out analytically, we use a simulation to do it. And we do it in such a way that it divides out. We never actually have to know the partition function. And so I spend 2 days deriving partition function. Then we spend another 2 days on chapter 6. Then I spend another day on chapter 7, all to tell you that in the end, what we do is just stick it all in a computer and simulate it. And we bypass having to calculate this. And so I don't know what's best. I want to get to simulations rather than focus on statistical mechanics as much. If I want you guys to learn statistical mechanics, then I would
Maybe just go over what all the variables in the partition function are rather than its derivation.
Here's what I think I want to do. Will you guys read chapter 5 to the derivation of the canonical partition function? Get down to this. Now, it's actually very powerful because if I know Q, you can see from this table, if I know Q, I can calculate any thermal property I care about. I can do heat capacities, I can do entropies, I can do even Helmholtz energy, and from that Gibbs energy, chemical potentials. It's very powerful. If I know what Q is, then I can calculate with partial derivatives every useful thermal property I care about. The challenge is getting to Q. So I want you to kind of do what we did with the last class. I want you to, or what we did with quantum mechanics, where I had you read through and then we just kind of talked about some things. I want you to read through the definition or the book of how to calculate out the partition function. And I'm going to post a few reading questions so that you can kind of focus on the important things. And then I think once I get you to the partition function, I'm never going to have you derive a partition function. I don't find it super useful once you've decided what it is, but I want to focus on how you use it. Okay, so I want you to read through here and then also read through actually this part of going from how you get to the classical definition of the partition function. Okay. Now, I want to talk about a couple other things as you're starting to run through here. I think on Learning Suite, I hope I've got this on Learning Suite. If not, I'm going to post it. I have some supplementary PDFs here. So in the chapter, it talks about Hamiltonian mechanics because we use Hamiltonian mechanics to derive the partition function. And we kind of talked about that in day 1 or day 2, how we think in terms of Newtonian mechanics, F equals ma, but Hamilton came along and he said, you can formulate equations of motion a little differently, called these equations of motion. And then I have an example here of how you can solve the same problem using Hamiltonian, it's a spring, or using Newtonian mechanics. It's just a differential equation both ways. So when you get to this idea of Hamiltonian thing, if you're stuck, go to my little example of how you can solve both Hamiltonian and Newtonian mechanics on that. Okay. And then also on Learning Suite, if I could get there, there we go. Ensemble averages. It talks about, it spends a lot of time here on ensemble averages. This is actually a great example I want you to go through. This is an ensemble. You can do different averages. So it talks about how many, it takes some sample data from a city, and it says how many pets each family has and how many children each family has, and it just counts them up. And so make sure you go through this example, and then if you need a little more how that relates to a macro or a microscopic system, I got this little diagram. So how to relate this kind of macroscopic to the microscopic. Undetermined multipliers. You'll need to understand undetermined multipliers a little down here. When you derive the partition function right here. And it talks about, this is all very esoteric. Undetermined multipliers is a way to optimize a function. And so I give you an example. Let's say, what's the largest volume of the rectangular box that can be placed inside of an ellipse? So you've got an ellipse here. And what's the biggest volume you could get if you constrain the sides to be on an ellipse, or the corners to be on an ellipse, right? It's just an optimization problem. I could have given you a different optimization problem. I think in the homework, I say something like, if I'm building a silo, like if you're in the Midwest and you got to store your grain, I don't know if you guys know about this, but you want to reduce heat transfer. And so either it doesn't freeze, or also so that it doesn't heat up and auto combust. You know that if things get too hot, they can combust. Hay can combust also, just kind of sitting around. Anyway, if you want to reduce heat transfer in a silo, a grain silo, you want to minimize the surface area while maximizing the volume. So what size do you want to give that then? You can optimize that, right? Minimize surface area while maximizing volume. That's it. Undetermined multipliers is a way to optimize a function. And I just go through with this and show you a macroscopically kind of this, how you would get how you could use undetermined multipliers to solve the maximum volume on an ellipse. It could be something else. We use undetermined multipliers to find the most likely states microscopically. But this is microscopic, this is more macroscopic. So if you need a little more, I've given you a little example. And then I talk a little about histograms. Oh, sorry, that's not actually what I want here. And then I give you a fairly detailed, some notes here. Actually, I'll post in my notes of what a partition function is, the derivation. So this is the derivation. It covers like 1, 2, 3, 4, 5 pages or whatever. And then I give you some more examples or a little different take on the derivation. So that's what I want you to do. And I got to remind myself to post the completed partition function derivation, because I was going to go through it in class, but I think it will be better for us if you read through this and then we talk about where you're confused so that we can get onto the applications later. And again, I'm never going to test you on this derivation, but it is useful to kind of know where it comes from so you understand why it's important. Okay. Let me give you a couple other ideas. When we derive the partition function, you get something that looks like this. This is probably what you got in PChem. It's a summation over all the Boltzmann weighted energy states. All the different ways I can move the system and get the different energies. This is quantum mechanically, because I can do different states, right? I can fix the state. But if we want to go to classical or classical movement, right, or to macroscopic, then I have to take this and change this into an integral. And when I change this into an integral, I also have to take into account Heisenberg uncertainty and a few other things. And that's what this section talks about, the classical canonical partition function. So it first talks about this bottom is your partition function. And then it talks about how to move to an integral from a discrete state. And then it talks about how this n factorial and this h to the 3n, can you see that on my screen? Change because of Heisenberg uncertainty and overcounting. And so I just kind of wanted to tell you that so that you can get the gist. To move from this quantum mechanical derivation that we did of the partition function to classical continuum integrals, you have to add in an n factorial, an h to the 3n, this is Heisenberg uncertainty, and then instead of energies, you have the Hamiltonian here in your integral. And so that's what I kind of want you to look for here, is how do you go from a discrete summation over energy states, EJ, to an integral in continuous space. And so the energy becomes a Hamiltonian, the kinetic plus potential. And then you have an n factorial and h to the 3n, which are related to some things that it describes here. One is the uncertainty principle, one is overcounting. Okay. So that's what I want you to look for there. Tyler.
So one thing that's confusing is you sometimes use the Hamiltonian as an operator, like it changes a function, and sometimes you seem to use it as a function, like you talked about taking its derivative.
That's right.
How do those reconcile? Because I can't imagine taking the derivative of like a plus sign, but this Hamiltonian of an operator.
Yeah, you kind of got to keep track of it. This Hamiltonian is a continuum function, right? It's just kinetic energy plus potential energy. It's the non-operator. The operator is when we solve out Schrodinger equation. And so none of these H's here, you could just replace these with total energy if you want, kinetic plus potential energy. Okay.
How does the operator form relate to the function form? Are you just replacing the like momentum and
the operator form, right, is you take the derivative of something when it's just kind of definition wise, this Hamiltonian just says it's the kinetic plus the potential energy. And they are kind of related, right? Because the way I get the kinetic energy is I need the velocities. And so in quantum mechanics, the way you get the velocities, right, is you take the derivative with respect to time of those particles. That's why it's an operator. And then, so they are related, but here just think of this as kinetic energy plus potential energy, total energy of the system. When you deal with the quantum mechanics, think of it as an operator, a derivative.
So am I right in thinking that the Hamiltonian, like the function or the energy for a quantum mechanical system would just be the operator applied to the wave function? So like if you perform the operator on the wave function, it would return the Hamiltonian like value there, or like the Hamiltonian.
Yeah, so if you take Schrodinger equation, H operator, usually we put a hat over it. H operator psi equals energy psi. If I operate on there, right, I'll get the energy out times my wave function. So if I take this mathematical function that I have for my wave function, I multiply it by the Hamiltonian operator, which will take derivatives in x, y, z, and the potential energy and all sorts of stuff like that, then it will give me the energy state times the wave function back. Here, it's not an operator. It's just saying this is the total energy of the system. Okay. Then this is going to be good. I want to get to simulations faster in this class. And if we can get through this little stat mech part faster, I usually have a test. I don't think I'm going to have like a whole full-fledged test on statistical mechanics. We are going to get to simulations and do more projects. Okay. I think that's all I've got today. I want you to start reading, and we'll pick this up next time and get through all of chapter 5, and we're going to start chapter 6. And if you've gotten through chapter 5, chapter 6 is fairly straightforward to get through. Any other final questions before I let you go? Graduate students, I think we got, I think we have graduate seminar, right, at 11, but Kyle, did you have a question?
Yeah, I'm curious what program are we going to be using for simulations?
We're going to start simulations. I am going to give you an option. I want you to get the basics down. So I've got a C code, and I'm going to try to write a Python one before we need it. I've written lots of molecular dynamics simulations. I've written them in Fortran, I've written them in C, I've written them in C++, and I've written them in, I've written multiple ones in C because that's my main programming language, because I keep thinking, oh, I could make this better, or oh, this would be better if I present it like this for teaching, but I can make it this way faster. So I got multiple codes. In fact, you can see one of them down here on Leonard Jones code in C. You could start seeing that. But The book has it in Visual Basic, so you could use it with Excel if that's what you want to do. I've got it in C, and I'm going to try to make a Python. So we should be able to cover most anyone, because I don't think anyone here knows Fortran. Does anyone know Fortran? And I think anyone here would rather code in Python or C or VBA than Fortran or some other thing like Ruby or whatever.
Okay, so we're I guess going to be using actual code and writing that ourselves rather than using like GrowMax or something.
So I hope towards later in the class, like when you do your project, you can definitely use, I'm going to introduce you to LAMPS or Charm or GrowMax or whatever. And you can use that for your project. That'll be one of the options for the project. What do you use in your research right now?
I use GrowMax.
Yeah, you could keep using GrowMax. I'll probably introduce LAMPS. So what we're talking about here, you guys, is there's different molecular dynamic codes out there. LAMPS is one made by Los Alamos, so it's like an acronym. Los Alamos Massively Parallel Molecular Mechanics or something like that.
Actually by Sandia.
What was that?
It's actually by Sandia. That's the one.
That's right. That's right.
Large scale molecular atomic.
That's right.
Parallel simulator, I think.
When I did most of my research, these weren't really around for bio stuff, so I wrote my own and just used force fields. But for bio side, there's something called CHARM or AMBER. CHARM is Chemistry at Harvard Molecular Mechanics. So it was a Harvard program. AMBER, I don't know what it stands for, but it's a competing one that came out of a different university. There's one called, kind of the hip one right now is called Blue Humd, because it's written in Python, but Python's slow. So it's actually just the front end's kind of written in Python and everything else is written in C. There's GrowMax that Kyle uses. GrowMax used to be the fastest one. It comes from Europe somewhere, maybe Germany. I can't remember. I think it's Germany. But it's kind of their version. And then there's actually proprietary ones that you pay lots of money for. So there's I don't know if you guys have ever heard of D.E. Shaw. Do you know that? D.E. Shaw is a company in New York that basically it's a smart guy that's rich that will just work on any hard problem. And you got to be actually really smart to get hired there. They ask you some crazy questions during your hiring process. They want to see how fast you can think on your feet. But they made a microchip specifically with instructions to do molecular dynamics. And they wrote a code just for that. So they don't use Intel chips. They use their own proprietary microchips. So theirs are incredibly fast, but they don't share them, right? They don't share their codes and they don't share anything. They want you to pay them to do stuff. So there's all sorts of stuff out there, but in my group, we use LAMPS because it's fairly fast and it's free and it's pretty easy to change how you need to change it. GrowMax and LAMPS kind of used to trade off for speed, but GrowMax was kind of single processor quickness. And LAMPS was more if you have a really big system and you want to do parallel. But now with GPUs, everything's kind of crazy now that there's no one super fast code anymore. Do you know what I mean by GPUs? Graphics cards, graphics processing units. So graphics cards, like in your computer, they are very fast at just doing math. They don't like doing decisions, if-then statements. And so when you're doing your computer, normal stuff like on your Windows machine or your Apple, it has lots of if-then statements, right? If I click here, or if I click here, if I do this or do that. So Intel chips or other types of x86 processors, they do if-then very well. But then graphics cards came along and say, well, if I need to play a game, I'm just trying to do the graphics. It's just straight math. I'm not doing any if-then statements. It's just pushing through a lot of vector calculus to make graphics, right? And so they came up with graphics cards. But what we found is that even though in molecular dynamics simulations, we do a few if-then statements, we do so much math that we just like using GPU. And GPUs have revolutionized both quantum chemistry and molecular dynamics. And everyone wants more GPUs. but you want codes that run GPUs. So Lamps had to write new code to write GPUs. GrowMax, I think they've started doing that. So you got to write your new code to use GPU instructions rather than just normal C. So that's the trade-off there.
So do you know if you can do coarse grain models on like with any of the programs?
Yeah, we use coarse grain on Lamps. That's why we use Lamps, because it's very easy to change. So we've got coarse grain from our model and other models in Lamps, and that's why we use it. I still have my code around, but it's not GPU enabled, so I don't use it anymore. I can't keep up with all the developers like Lamps or GrowMax or Amber have, right? They hire programmers just to keep up their codes. Okay, let's meet back next time. We'll talk about partition function. Make little notes, say, I don't quite understand why it did this, or help me here, so that we can go through this derivation of the partition function. Thanks, everyone.
Thank you.